This week we're learning about the planets, and we divide the planets into two general types. There are the terrestrial planets that are like the Earth, and in many ways, and there are the Jovian planets that are like Jupiter in many ways. You might think of the Jovian planets as the gas giants. And so we're going to cover those in the next video and focus in on the terrestrial planets in this video. So before we get into the details of the terrestrials, let's just take a quick look at the solar system as a whole and understand its structure. Most of the matter of the solar system is concentrated into the sun, which is at the center. The planets that we're going to talk about, that we're going to focus on, are immediately surrounding the sun, but there is an extended solar system that goes beyond that. And so if you look at the picture in the upper right, you can see the orbits. The blue paths are the planets, and then there are some dwarf planets like Pluto and asteroids in red. So those other orbits are asteroids. Within the solar system, there are there's the sun, there's the planets, there's dwarf planets, there's asteroids, there's comets. And if you move out from the center, you go from the sun, Mercury, Venus, Earth, Mars, and then between Mars and Jupiter, there's a belt of asteroids called the asteroid belt. And then if you go all the way out beyond the orbit of Neptune and Pluto, there's a larger asteroid belt known as the Kuiper belt. So now look at the bottom right picture. The Kuiper belt surrounds the planets of the solar system, and it's contained with many, many, many asteroids. Now, if you go beyond that, and so everything inside the Kuiper belt, including the Kuiper belt, is spread out into like a flat disk, essentially a flat disk. If you go beyond the Kuiper belt, there's a bubble that surrounds the entire solar system called the Oort cloud, which is contained primarily with comets. Okay, and so there's this bubble surrounding the entire solar system. Notice the scale here. So this Kuiper belt is now in here. All right, so that's the basic structure of the solar system. Sun, planets, asteroids, dwarf planets, more asteroids, and then a big bubble of comets. Now, solar systems like ours are not unique. Well, they might be unique in one very important way, that is the only one that has people. But they're not unique in the sense that you get planets and asteroids and comets. We expect that that's very common among the stars. So we can think of every star in the sky as a potential solar system. And if you look in one spot in the sky, in the Orion Nebula, that is a star-forming region. Stars form from what are called molecular clouds. They're big clouds of dust and gas that by gravity condense and eventually form into stars. And around those stars, planets, asteroids, and comets. Now, the Orion Nebula contains many, many potential solar systems. And so here's a sampling. These pictures here are a sampling of stars in the initial stages of formation, what we call protostars. So they're not quite stars yet. We'll talk about what makes a star and a protostar not quite a star later on, but it's not there yet. It hasn't totally formed into a star, but it's beginning to. And you can see that they're surrounded by dust and gas, and that cloud of dust and gas has not yet formed into planets. If planets did start to form around these stars, and we expect that basically all of them would eventually have planets surrounding them, we would call those planets exoplanets. So an exoplanet is a planet around a star other than the sun. And there are actually active searches looking for exoplanets among the stars. It's easier to find planets like Jupiter, but we've also found some Earth-sized planets out there as well. And the theory would be, because stars form in basically the same way, that any star forming from a cloud of dust and gas is going to develop planets around it. Now, taking a look here at the properties of the terrestrial planets and also including the moon. There's a lot of numbers on here. I don't by any means expect you to memorize these numbers, but I put it up here for a couple of reasons so we can make some comparison and contrasts between them. And this is something you can refer back to. But let's just go down each column quickly. So in terms of mass, just look at the power of 10. 10 to the 23rd, 24, 24, 23rd, 22. Okay, so the moon is smaller than the others. It's about, 10 times smaller than Mercury. And the Earth and Venus are very similar. Mercury and Mars are very similar. Venus and Earth are about 10 times bigger than Mercury and Mars. Okay, so there's a range in sizes, with the Earth being the largest and Venus being a close second in terms of mass. In radius, the story is pretty similar, similar radius for Venus and Earth, and similar for Mercury and Mars, although Mercury is smaller, and the moon is smaller still. Notice that these two categories, and in fact this one, and then also atmospheric pressure, they're often given in terms of Earth. This goes back to the idea that we always want to have something to compare it to, and when we're thinking about planets, the natural thing to compare to is the Earth. So in these units, Earth would be a 1, which is another way to look at this. Venus is about 82% of the mass of the Earth and 95% of the radius of the Earth. Density. Now, density is going to tell us about what the object is made of. Density is mass per cubic meter, so it's the amount of mass contained within a cubic meter of the material. Planets are made of many different things, so they're not uniform composition. If you've studied Earth science at all, you'll know that there's different layers to the Earth, and that means it's not uniform in density, but on average, its density reflects what it's made of. And these planets are made of mostly like rocks and metal, and so they're relatively high density. For reference, an average density of 1,000 would be water in these units. So we're talking about objects here that are much more dense than water. They're not liquid or gas, they're made of rocks and metal. Now, Mercury, Venus, and Earth, they're fairly similar, so you could gather from that they're made of similar materials. Mars and the moon are, on the other hand, a little bit lighter material. So the rock of these planets is a little bit lighter, and that's interesting. Why would they be different? If they're made from the same protostellar disk, why would they end up a little bit different? It just has to do with how the rocks and metals are differentiated as they separate. In terms of the Earth and Moon, there's a longer story to that that has to do with the Moon's formation by a giant impact with the Earth, and the Moon collected the material that was on sort of the outside. If you think about it, heavier material tends to sink towards the center, and so the Moon is mostly made up of like upper level material, which is a little bit lighter. For Mars, I haven't studied this problem that much. I have a guess that maybe because of its proximity to Jupiter, Jupiter took some of the metal and rock material that would have been heavier and left Mars with a little bit less to collect in it, so its density is lower. But that's my speculation. Okay, surface gravity tells how strong the gravity would be, how heavy you would feel if you were on that planet. Venus and Earth, you'd feel similarly. Mercury and Mars, you would feel much lighter. So you'd only weigh about 38% of what you weigh on the Earth. And on the Moon, it's about 1/6 of what you would weigh on the Earth. Escape speed, this is how fast you would need to be going to escape the gravity of that planet. And it's going to be related to the surface gravity. So these numbers kind of scale appropriately. Venus and Earth are similar, Mercury and Mars are similar, and the Moon is lower. Rotation period. Now, this is an interesting one to think about. This has to do with how fast they're moving in their rotation, so how long a day is. And so this is this is a property that would have a lot to do with what life would be like on that planet. Not that these other ones wouldn't, but we think of our daily lives. Well, this rotation period determines what a day is. And so on Mercury, a day is 59 days. That means it would take 59 of our days for someone on Mercury to experience one day on Mercury, one cycle of day and night. On Venus, it's even stranger. It's negative 243. Now, the negative just means that it's rotating in the opposite direction, so it has a retrograde rotation. All the other planets rotate in the same way. So viewing from the northern biased perspective, they rotate counterclockwise. Venus rotates clockwise. And so because of that and its orbital period, it only goes through a day-night cycle once every 243 of our days. Earth and Mars, on the other hand, are actually very similar in this respect. Just a little bit longer. It takes a little bit longer for Mars to go around. And on the moon, it's about a month. So that's the tidal syncing between the Earth and Moon, that it takes about a month for the moon to rotate around and about a month for it to orbit around the Earth. Surface temperatures. Surface temperatures are widely varying among the terrestrial planets, and on Mercury it's widely varying just within that one planet. And you might be able to guess why if you think about it. Mercury is close to the sun, so you'd expect that it has very, very hot temperatures. But if you look over at this category, it has no atmospheric pressure. Mercury has no atmosphere. It means it can't retain its heat. So the side that's facing the sun is extremely hot, 700 Kelvin. But the side facing away from the sun is very cold, only 100 Kelvin. And that's the value of having an atmosphere. It helps you keep your temperature constant. Venus has 90 times the atmospheric pressure that we do and a uniform temperature of 730 Kelvin. On Earth, we have slight fluctuations in temperature, but on average, it floats around 290 Kelvin. Mars has a small atmosphere, but doesn't retain a ton of heat, and so it has pretty wild swings in temperature. Not as extreme as Mercury, but from 180 to 270 Kelvin. And similar story for the moon. No atmosphere to speak of on the moon, and its temperature also varies wildly from 100 to 400 Kelvin. So it can actually be hotter on the surface of the moon than on the Earth, or much, much colder. Okay, going into the interior of these planets. Each of the planets has a set of layers: the crust, the mantle, and the core. And in the core is where you'd find the most dense material. In the crust, you'd find the lightest material, least dense material. But what I'm really interested about here in this image is the activity inside the planet, because that affects what the planet has going on its surface, the activity from the inside. And that has to do with a layer called the lithosphere. And the lithosphere goes from the crust down to some depth within the surface. So on the Earth, it's from here to here, right? This dotted line indicates where the lithosphere stops. On Venus, from here to here. Then from Mars, here way in basically to the core, Mercury basically into the core, Moon basically into the core. Now the significance of that for these three planets is that their lithosphere is so thick at this point in time that material, magma, from inside the planet can't make its way to the surface. So the lithosphere layer is really like a dead rock layer. It's not geologically active, and so the material from within can't make it to the surface if the lithosphere is too large, too deep. And so Mars, Mercury, the Moon, they're no longer geologically active, and their surfaces are not going to change unless they're impacted by asteroids and meteorites, and those things are the only ways to change the surface structure. Mars has a little bit of an atmosphere, so there can be a little bit of weathering. But otherwise, what happens on those planets doesn't change. There's no erosion. There's no volcanic activity. On the other hand, Earth and Venus are both very geologically active planets. And that's because their lithosphere is fairly thin. And so the material, all the activity that's going on around the core can seep out into the surface. There's volcanic activity on both planets. On Earth, we have earthquakes, and then there's lots of weathering, obviously, from the atmosphere. Okay, so this diagram has to do with our observations of these inner planets from the Earth. And in particular, for Mercury and Venus, if you're looking for those planets, they're always going to be within a short distance of the Sun. And that's because their orbits are interior to the Earth. And when the orbits are interior to the Earth, as you can see on the diagram, there's a maximum angle that those planets can get from the Sun. For Venus, that maximum angle is 47 degrees. So you'll never see Venus more than 47 degrees from the Sun. Now you might see it much, much closer. So if Venus was here, the angle would be really small. If Venus was over here, the angle would be really small. But it won't get any bigger than 47 degrees. For Mercury, it won't get any bigger than 28 degrees. And so within 47 degrees of the Sun, you'll always find Mars and Venus. You'll either find them shortly before sunrise or just after sundown. Those are the two times of day where you might find them. And then that just depends on which side of the Sun they happen to be on. This angle is referred to as the elongation of the planet. And so Venus has a maximum elongation of 47 degrees, and Mercury has a maximum elongation of 28 degrees. For the outer planets, and the only other one that's shown here is Mars, they would have maximum elongations of 180 degrees. So they could be anywhere within 0 to 180 degrees from the Sun, basically anywhere along that circle. And that's also true for the other outer planets, Jupiter, Saturn. They're also maximum elongation of 180 degrees. All right, so a little bit on Mercury's orbit here. It has a strange thing going on where it has a resonance in its rotation and its orbit. It's not quite tidally locked with the Sun yet. If it was tidally locked, its day would be essentially infinitely long. It would always have the same face facing the Sun, like the Moon is to the Earth. But Mercury's not quite there yet. It was once thought that it was, but 1965 we learned that it's not. Instead, it's in a 3-2 resonance. So it rotates around 3 times while it goes around the Sun twice. And so that's the situation. It has basically 3 days for every 2 trips around the Earth. So its year is like 1.5 days long. I can go through this quickly because we talked about this on the table slide. All the planets, if you view them from above, are rotating around counterclockwise except Venus. So this is what I meant when I said Venus has retrograde rotation. It's rotating clockwise when viewed from above. Now you'd have to ask why that is. Now first maybe you'd ask, well, why aren't they just random directions? Why couldn't planets rotate in any direction they want? Well, what you'd think about is how the planets formed. They would form in a disk. The disk is all rotating in the same direction. You'd expect that everything forming within the disk would also be rotating the same direction. And so the expectation would be all of the planets are rotating counterclockwise. Venus is not. Earth is tipped over. Mars is tipped over. So we have to have an explanation for how this could be. And the best explanation we have for these things is that in the early stages of formation, they collided with other things. Asteroids were abundant in the disk of the solar system, and so there were probably massive collisions that knocked these planets over so that their axes don't all point perfectly straight up and down. And for Venus, something must have happened where it actually collided so strongly that it started spinning the other way. All right, so now we're going to take a closer look at each planet, each of the terrestrial planets individually. So first, Mercury. What probably catches you with the image here on the left is that Mercury looks a lot like the moon. It's got a gray cratered surface, no atmosphere. It's not too much bigger than the moon. It's a lot like our moon is. Its craters are actually named after famous artists, composers, and writers. So there's a crater Matisse. And the surface of the planet is easy to mistake for the moon's surface. If I just showed you this picture and said, what is this, as a test question, that would be kind of an unfair question, because you could reasonably argue that this looks just like the moon. There are a couple of notable features, and we're going to look at one here on Mercury. This is called Caloris Basin, this orangish colored region here surrounding the crater here in the middle. It's a fairly large impact crater on Mercury, and this orange region is a blanket of dust that ejected from the impact, and it created a concentric ring of mountain ranges surrounding that crater. And so just like the moon, it has craters and mountains that are a result of those impacts. On to Venus. Now, we've already seen that Venus has a lot of similarities. And if you look at a planet picture, you could imagine that that planet hosts life, and there's certainly been a lot of speculation about that throughout the years. It has clouds and what appear to be similar geography to the Earth. Its maps look like a world that we're familiar with. But it's not very habitable, not at all. It's extremely hostile. I've already mentioned that its atmospheric pressure is 90 times ours. We couldn't survive that alone. Its temperature is over 700 Kelvin. That's not manageable. And its air is not oxygen and nitrogen like ours is. It's mostly carbon dioxide and sulfuric acid. So we'll get into a little bit more on that in a minute. Some closer up images of the surface, we see that the results of that, the temperature and pressure conditions and its geologic activity, you have a lot of these lava features, lava domes, and the surface is really covered in this type of activity. There's only been one mission to successfully land something. This was the Soviets in 1982, the Venera mission. They landed something. It only survived on the surface for about 2 hours. I think it was only designed to last for maybe even a half an hour. The expectations were not very high for how long this could last because of the extreme temperatures and pressure. But it did last for a couple of hours, and we did get a few pictures of what the surface looks like on that planet. Now, the reason why Venus is so hostile as an environment ultimately has to do with one thing, and that it doesn't have water on that planet. Now, you can think of why that might have happened. It's closer to the sun. It did not have ozone layer to protect it from UV radiation. And so because of that, it's you probably don't know this, but ozone protects us from UV, and UV can destroy water molecules. And so over time, any water that would have been on Venus would have been destroyed. Now, the reason why that's important is that water can absorb carbon dioxide. And so on the Earth, this is part of the greenhouse effect, that there are greenhouse gases like carbon dioxide, and the ocean helps us regulate them. And the greenhouse effect is a good thing for us on Earth. It allows us to keep the temperature at a habitable level. If you don't have water to absorb greenhouse gases like carbon dioxide, then what happens is those gases just pile up instead of there being a regulation. It's just a runaway greenhouse effect. More and more greenhouse gases are building up in the atmosphere, essentially like piling more and more layers of blankets on the planet. And as a result, Venus has a much thicker, much higher atmospheric pressure, and its temperature is accordingly much, much higher. We call this a runaway greenhouse effect. So the source of Venus's inhabitability is ultimately the lack of water and this runaway greenhouse effect. So it's an extremely hot, hostile environment. Now, another way to see how stark this difference is to take a look at the map of volcanoes. So look at the upper right first. The upper right are the volcanoes on the Earth. They're mainly located along the plate boundaries, and so the friction of the plates has caused places where magma is free to come up through the surface. Volcanic eruptions produce carbon dioxide into the atmosphere. We have a significant number of volcanoes on the Earth, but it's nothing compared to what's on Venus. So the picture on the bottom left is a map of volcanoes on Venus, and you can see that it's entirely covered with volcanoes. And so the extreme amount of volcanic activity has dominated the atmosphere of that planet. Okay, on to Mars. Mars has an interesting geography. It has some very big features. And part of the reason why it has big features is that it has lower gravity than planets like Earth and Venus. And so with lower gravity, there's less of that kind of pressure to keep things close to the surface. And so on Mars, we have large gases in the planet. This is the Valles Marineris. It's much larger than the Grand Canyon. It's a big, almost a wound in the planet. And then there's this Tharsis Bulge, which is the size of North America and an elevation of 10 kilometers above the surroundings. So extremely tall mountainous range in this region. It's believed that it once had active volcanoes, but these volcanoes would be extinct at this point in time. Mars is no longer geologically active that we know of. We have visited Mars more than any other planet besides the Earth, because Mercury's so hot being close to the sun, that makes that one challenging. Venus, we've just talked about its challenges. Mars doesn't have either of those problems. It's much cooler and no atmosphere to deal with, so that makes it easier to explore. And so we have lots of good pictures of what the Martian surface looks like from landers and rovers that have been placed on the planet. What we found is that there's a big difference between the north and the south. In the north, rolling volcanic terrain. In the south, heavily cratered highlands. So there's some significant difference between those two. The south is actually much taller. South is 5 kilometers higher on average than the north. And so the assumption is that the northern serpent is actually younger, meaning it was geologically active until more recently than the south. So geologic activity, for some reason, lasted longer in the north than in the south. Okay. Mars is home to the largest volcano in the solar system. It's called Olympus Mons, or Mount Olympus, appropriately. And you can see here the picture of Olympus Mons compared to Mount Everest. Now, it is the biggest, but it probably would not be as hard to climb as Mount Everest because its slope is much more gentle. Its surface is elevated way higher than Mount Everest, but it's never as steep as Mount Everest, or Mauna Kea, which is, I think, bigger than Mount Everest if you include the part that's submerged underneath the water. Okay. Now here's a surface terrain map of Mars, and you can see the difference, the south being much higher elevation than the north. And this also shows a lot of the locations where landers have gone to explore the surface: Opportunity, Pathfinder, Viking 1 and 2, Spirit. You can see there's a lot of big features like the Tharsis Bulge and Hellas Basin down here. Valles Marineris is over here. But the big takeaway that you get immediately from looking at is like the north is much lower in elevation than the south. And so you might speculate, well, maybe the north used to be a ocean. Looks like that would be possible. And so there's always been a lot of speculation about water on Mars. And we see features that look like this, that look like erosion from either water or atmosphere. And so it's easy to start dreaming about what Mars used to be like compared to what it is like right now. Okay, so here's a few more pictures of evidence that looks like water. Now, this picture here is on the Earth. This is a picture of the surface of Mars, and the similarities are obvious. This is a runoff channel on the Earth. Maybe this was a runoff channel that's now dried up on Mars. This looks like the result of a flood. This looks like a river delta. Now, we can't say for sure what these things are just yet, and we haven't confirmed directly that there's been water on the planet, but there's a reasonable confidence that we will one day discover that these are results of water flow on the planet. And last thing on Mars, just this is a neat fact that we happen to have one of our satellites looking at this cliff. Now, this is a cliff made of frozen carbon dioxide. It's not ice. And we happen to be looking at it just at the moment that there was an avalanche. And so we got a neat time-lapse picture of the avalanche happening in real time. Okay. Now, lastly, on the terrestrial planets, I just wanted to survey some of the moons that are out there, so you can have a look at the significant moons in our solar system as well, which are also terrestrial worlds. For Jupiter, we've done a little with these already. These are the 4 Galilean moons: Io, which is volcanic; Europa, which may have a subterranean ocean; and then Ganymede and Callisto, which are more similar to our moon. For Saturn, now it's got some reasonably large moons, and then one which is the largest moon in the entire solar system, called Titan. For Uranus, no majorly large moons, nothing comparable to our Earth's moon. For Neptune, there's one that's similar in size called Triton. So the moons that I would like you to remember: Jupiter has these 4 Galilean moons: Io, Europa, Ganymede, Callisto. Saturn has Titan, Neptune has Triton, and Earth has the moon. So these 4, 5, 6, 7, these 7 moons are the largest moons in our solar system, and the one that you'll see the most interest about in popular articles. And so I thought it would be worthwhile to at least mention them here because they are terrestrial worlds. And I was just talking about water on Mars. It may be Europa that has the most interesting things to do with water. If our theories are correct about Europa, it has an entire ocean of water underneath its surface, and it may actually have more water than the Earth does. Now, what makes that really fascinating is that everywhere on the Earth that we've found water, we've found life. And so there's a reasonable theory that suggests that there may be microbial life existing on Europa. And who knows, we might find it in other places as well. Titan, which has its own atmosphere, and we've only explored that a little bit. That may also offer some really interesting discoveries.